You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Nikodem Popławski. Dr. Nikodem Popławski is a distinguished lecturer and coordinator of physics at the University of New Haven. He earned his Master of Science in Astronomy from Uniwersytet Warszawski in 1999 and completed his PhD in Physics at Indiana University in 2004. He is renowned for his pioneering work in theoretical physics, particularly his hypothesis that every black hole could serve as a gateway to another universe, suggesting that our own universe might exist within a black hole in a larger cosmos.
Dr. Nikodem Popławski, welcome to the program.
Thank you.
Now, Doctor, your work is very intriguing within astrophysics in that in some respects, the universe does resemble a black hole. There's reasons to see parallels there. However, you have looked into general relativity deeply and realized that, well, actually a black hole could be a gateway to a sort of parallel universe in a way, or a child universe of this one, and maybe this one is a child universe of another universe. Could you give us a rundown of your hypotheses here?
Yes, certainly. So Einstein's general theory of relativity, which is one of the pillars of modern physics, is a very successful theory, being confirmed in many experiments and observations. However, there is one prediction, the existence of singularities. Singularities are the points or sets of points of space-time where curvature of space-time and density of matter are infinite. And this means that physics breaks down because we can never measure anything which is infinite. We can only measure quantities which are finite. So I tried to see whether this existence of singularities could be avoided. And there is the oldest extension of general relativity, which is called Einstein-Cartan theory, although some physicists call it general relativity with spin and torsion. It was proposed by Cartan in 1921, which is 5 years earlier than Schrödinger equation of quantum mechanics. In the 1960s, two physicists, Sciama and Kibble, they discovered that space-time torsion can be created by intrinsic angular momentum of matter, which is called spin. Spin of fermions, which means quarks or electrons or neutrinos, can create torsion. And then in 1970s, several physicists discovered that torsion generated by spin of matter acts like repulsive gravity. So what happens is that at extremely high densities, much higher than neutron stars or nuclei, torsion manifests itself like a gravitational repulsive force. So when the matter is compressed to the very, very high density, it will not reach a singularity. It will not compress into an infinitely dense point. Just before that, torsion would become very strong and would oppose the indefinite compression. Torsion would stop the contraction of matter, and instead of singularity, the matter would compress to something very, very dense and hot, but still finite. Everything is finite. There's no singularity. And those physicists applied this idea to the beginning of the universe, replacing the Big Bang, which is supposed to be singular, with something non-singular. What my contribution was, I applied Einstein-Cartan theory of gravity, the general relativity with spin and torsion, to the formation of a black hole. And I found that when the matter collapses and forms a black hole, so the event horizon is being formed, which is the boundary of the black hole, and inside the event horizon, or maybe I should say on the other side of the event horizon, because there might be something much bigger than the event horizon on the other side. So it is the other side, not the inside. And I found that the matter in a black hole which formed does not contract to a singularity. Instead, it stops the torsion becomes very strong, so it opposes the contraction. The collapse stops, and because space-time cannot be matter in the space-time inside the black hole cannot be at rest, which comes from the Einstein's equations of general relativity. And also the matter cannot come back through the original event horizon because motion of the matter through event horizon can occur only in one direction. So the matter cannot go back, cannot leave the black hole, and cannot be at rest. So after the bounce, the matter expands, and it has to expand into a new space. So mathematically, that new space is equivalent to a new closed growing universe on the other side of the event horizon. And that bounce of matter, which we can call the big bounce, is basically the big bang of the new universe, the new baby universe created on the other side of the event horizon of the parent black hole existing in the parent universe.
Is there a difference in mass? In other words, can we look at like a primordial black hole, the hypothesized black holes from the leftover from the formation of the universe, that idea, and say the same thing? Or are they too low mass? Is there a mass limit for the creation of a child universe?
So there should not be any mass limit, any black hole. So we have like three types of black hole as far as we know. We have the stellar black holes formed from the supernova explosions of dying stars. We have intermediate black holes, which we believe they exist at the centers of globular clusters. And we have supermassive black holes, which exist at the centers of galaxies. And we may have also primordial black holes, which were created like at the very beginning of the universe. So any black hole has the event horizon, so there is the other side. And in general relativity, singularity would form, but thanks to torsion generated by spin, singularity is being replaced by big bounce, and then the formation of the new growing universe on the other side of the event horizon. So every black hole, in my theory, every black hole would create a new universe. So it would be independent of the mass, although the mass of the original black hole, which created a new universe, probably would be related to properties of the new universe, of the new child universe. There's also one thing I want to mention. The universe obviously is much more massive than a black hole. Like if every black hole creates a new universe, then our universe was born in a black hole existing in some parent universe. But of course, our universe has much more mass than the black hole which created it. And this mass comes from intense quantum particle production near the big bounce, because we know from quantum field theory in curved space that strong gravitational fields which change in time very quickly, they create a lot of new particles, antiparticles. It's called the pair production. This is something similar to the Hawking radiation, that near the event horizon, there is the particle-antiparticle pair production. However, near the big bounce, those fields are much stronger. So this quantum particle production is very big, and very, very quickly at the big bounce, a new matter can be created in very huge amounts. So that's where the huge mass of the new universe comes from.
Now, this is very similar to the concept of the white hole. But in this case, if I understand your theory correctly, you're not going to see these appear in our universe, because the moment you go through that event horizon, you're cut off. It's somewhere else. Therefore, the reason we don't see white holes in this universe is because we are the white hole, and we're the only one.
Yes.
And that is the Big Bang. That is the universe. Am I getting that correct?
Yes. So if our universe was formed in a black hole existing in some parent universe, so we are already in our universe. So that parent black hole, which created our universe, from our point of view, would look like a white hole. It is the other side, because the other side of the black hole is a white hole. Black holes are solutions of general relativity. white holes are also solutions of general relativity, and Einstein-Rosen bridges, which are wormholes. Wormhole is like a combination of black hole on one side and the white hole on the other side. So in Einstein general relativity, only black holes can form. Now, white holes cannot just form by themselves in any theory, because the question would be where the matter comes from, because the motion of the matter can be from the white hole to us, so the origin would be unknown. However, wormholes, Einstein-Rosen bridges, are very natural, because the matter goes through from the parent universe to the child universe. So we are in the universe created by the black hole, and that black hole looks like a white hole because we see the other side. So if this theory is correct, we should see in our universe one and only one white hole somewhere, and we don't know where it can be, because it could be maybe quite close to us, but this may be very, very far away beyond the cosmological horizon, because our universe is expanding and it's accelerating, so we cannot see the whole universe. So maybe this white hole is in the region of the universe which is beyond, so we will never be able to observe it. So this would be the only white hole. And also, if this white hole is like far, far away, then we would not see it as it is now, because the farther we look into the universe, we see the past. Like, for example, when we look at the sun, we see the sun as it was 8 minutes ago, because light needs to travel 8 minutes from the sun to Earth. So if this white hole is far, far away, we would see its image from a long, long, long time ago, and we might still see some matter coming through, because after our universe was formed, there could be still some matter. This parent black hole could exist in the parent universe surrounded by some other like stars, and some matter would still be going. So we might see that, but first we would have to find that one and only one white hole.
But this isn't a permanent situation, right? In other words, we suspect that black holes evaporate through Hawking radiation. What happens to the universe on the other side, if there's one there? What happens to it as the black hole evaporates? That universe must still be there, right?
Yes. So yes, it's a great question. Actually, so in my opinion, I was like thinking about this because those are very natural questions. What evaporates is not the universe on the other side of the event horizon. What evaporates is the connection between the parent universe and the child universe. So that when the universe on the other side of the event horizon, that universe would be still there. It is event horizon evaporates, but event horizon is just the connection. It's just the bridge from parent universe to the child universe. So basically, when the black hole evaporates, child universe disconnects forever from the parent universe.
That has a certain poetic tone to it, that the universes, they're born, they're babies of a universe, and then they go off on their own.
Yes.
And then they spawn new universes. It's almost like nature and life in a way.
Yes, it is quite a huge analog. Now, of course, assuming that the Hawking radiation is correct, right now it is hypothetical, although it is analogous to particle production near the Big Bang. So there are strong theoretical arguments that this radiation is real.
Aha. So virtual particle production in Hawking radiation is an analog to what you were talking about then, in the production of matter in a Big Bang resulting from a black hole, right?
It is very similar process, because Hawking radiation and the particle production near Big Bangs, they both use a combination of quantum mechanics and general relativity. What happens is that in strong gravitational fields who are changing in time, and even although Hawking radiation does not require the change of time, because black hole can have the stationary event horizon and still it happens. So maybe the analogy is not quite exact, but there is some similarities. It is basically quantum mechanical effects in strong gravitational fields allow production of new matter, like through the pair production. So it can be either Hawking radiation or matter production at the Big Bangs.
Now, time. This is going to play into this, because you get near a black hole, you get near the event horizon, time dilates severely, as in general relativity. What happens when you go into that event horizon? In other words, does a new timeline start of sorts, or just a completely separate instance of time, separate from our time in this universe.
So gravitational time dilation is, of course, experimentally verified, the huge agreement with general relativity. What happens is that near the event horizon, at the event horizon, the time of the clocks, which are at the event horizon, relative to our time on Earth, or to be more precise, at the time far, far away where there is no matter. So it is like a Minkowski flat spacetime. So time of the clocks near the event horizon slows down to zero compared to time on Earth or far away from the black hole. Now, when time is relative, so when a spaceship goes to a black hole, then the passengers on that spaceship will not see anything strange with time. Their time will be running at a normal rate for themselves. It's called proper time. So they will not see any difference. However, their time will be slowing down relative to our time. So basically, if we meet again, then we would see those passengers much younger than us because they aged more slowly. So they will not see any difference. They will go through the event horizon. If the black hole is very big, it will be a safe trip because those tidal forces will be quite small. Small black holes have huge tidal forces which make the spaghettification of objects going through, but big black holes are quite safe. So they will not notice anything. The thing is that from our perspective, when we are on Earth and we will be watching this spaceship going to a black hole, we will never see that spaceship enter the event horizon going through, because from our perspective, their time will be slowing down relative to our time. So basically, from our perspective on Earth, time at the event horizon freezes. So we will never see anything going to a black hole, even though the objects going to a black hole, they will cross the black hole, they will observe that, but we will never see that. From our perspective, nothing will go into a black hole. The objects are falling into a black hole after infinite time. And because of that, we could make like a thought experiment. We can consider a star which is collapsing and forms a black hole. We can put a spaceship on the surface of collapsing star. And analogously, we will never see on Earth that star forming a black hole, because that spaceship will reach the event horizon which forms after infinite time, which means on Earth, we will never see any black hole forming. What we observe in centers of galaxies or like from supernova explosions, the black holes we see, they are not black holes yet. They are almost black holes. We know that they are black holes in their own timelines because the ratio of mass and radius of those objects satisfies the Schwarzschild relation, which defines a black hole. So we know that those black holes are black holes in their own time, but from the perspective of the time on Earth, those black holes are not yet black holes, which means not only we cannot ever, being on Earth, we can never observe the formation of the black hole and the event horizon, but we also cannot observe the formation of a new universe on the other side of the event horizon, because if the event horizon forms in Earth time after infinite time, then everything after forms after infinite time. So from our perspective, our universe is the only universe, because all these child universes in black holes and all the black holes have not formed yet.
They are always, from our perspective, in our future. Always.
Yes, in infinite future. We will never see them. If we are in our universe, if we stay in our universe, we will never see any black holes like formed. They are almost black holes, but we will never see a black hole formed its event horizon, and we will never see the new universe, because new universe is created after the formation of the event horizon. But when we decide to go, pick some black hole and go there, then we will realize that actually we can cross the event horizon, because now we are using different time. Now we are using the time which is there, not on Earth. And we cross the event horizon, and we can realize that on the other side of the event horizon, actually there is space which is much bigger than the event horizon. There is a new universe. It is like the analogy of like two doors. One door, the standard picture in general relativity with the black hole, with the singularity, is that the black hole is as big as the event horizon. So if you open the door, it is a door to a closet, and the closet is as big like as the door to the closet. But in my theory, the other side of the event horizon is already a new growing universe. And the analogy would be that you open the door, and the other side of that door is not a closet, but it's outside, door outside, which means you are going outside. You are going to a new huge space.
So to get this straight, we can cross that event horizon and go to another universe if we go there.
We can, but then we will never go back to our original universe, and we will never be able to send any information to Earth like what we saw on the other side, because everything, once we are on the other side of the event horizon, then we will never go back, and we cannot send any light signal or anything, because those things cannot go back.
Yes, essentially all Earth would ever see is just a gravity source and an event horizon.
Yes.
It is shrouded by the event horizon, and that's it.
Yes.
That's that.
And what happens on the other side can be seen only if someone wants to go to that black hole. So basically, from our perspective, the final future of the star collapsing to a black hole will be the formation of the event horizon, which will form after infinitely long time, which means never forms. So this is basically, that's it. And this is the maximum entropy also of the black hole. It reaches maximum entropy after infinite time, and the event horizon forms after infinite time. And this is according to the timeline of the time on Earth. However, when someone goes to the black hole, they can realize that they can cross actually the event horizon, and they see that the timeline can be actually extended more into the future, and entropy can increase even further, because now there's a new universe, new particle production, new matter is being formed, new black holes can be formed there. So the entropy actually can even increase further. So the second law of thermodynamics is satisfied.
And in a way, this analogs time itself. In other words, you can go into the future, but you can't ever go back. And again, with this being intimately related with time, it fits. So, it seems to make a certain amount of sense.
Thank you. Actually, what I want to mention is that, time asymmetry is like quite a mystery. Like, for example, like we can go back to the same space. We can go somewhere and come back. But in time only proceeds forward. We cannot go backwards in time. And I believe that the idea that black holes creating new universe explains the origin of this past-future asymmetry. Because when the matter goes through the event horizon, it falls into a black hole, then this motion is one directional, which means we can define future and past, because the matter always moves from outside to inside. So this corresponds to the matter goes from past to the future. So there is already the past-future asymmetry. The motion of the matter through the event horizon defines where is future, where is past. So at the event horizon, we have already constructed the future-past asymmetry. And because space-time is continuous, if the future-past asymmetry is already established at the event horizon, it has to be also analytically continued to all points within the event horizon, which means the child universe in a black hole will inherit that future-past asymmetry. So the time will be going only forward, not only at the event horizon, but also at all points in the new universe, which means also in our universe, because we are created by a black hole as well.
One of the great mysteries, Doctor, in astrophysics is the so-called fine-tuning problem, meaning that the parameters of the universe are just so for matter to exist, and even to the point of life on Earth and perhaps elsewhere. In this model, going to another universe, does it get fine-tuned by the universe that gave birth to the new universe? In other words, would that universe be fine-tuned to the exact parameters of our universe?
I believe it would have the same laws of physics and the same values of physical constants. Lee Smolin made this hypothesis. He also believed that every black hole can create a new universe, but his argument was slightly different. So he assumed the existence of singularities, and he said that the final singularity in a black hole can become an initial singularity, like the Big Bang of the new universe. And so there's like a transition from the final singularity to an initial singularity. So basically, this is the same singularity. Now, singularity means that things become infinite. So there's a discontinuity. Existence of infinity means all functions. Some functions can be discontinuous, and discontinuity allows the change of constants of physics. Because if something is discontinuous, why not more? And maybe laws of physics could be discontinuous. Instead of 4 dimensions, a new universe could have like 5 dimensions. However, I believe that because of torsion of space-time, there is no singularity. So the big bounce is non-singular, it's regular, everything is continuous, the space-time is smooth, there is no discontinuities. So because of torsion, I would think that everything is continuous. So there is no reason for constants of physics or number of dimensions or laws of physics change. So I believe that the child universe would have the same values of physical constants and the same laws of physics as our universe.
Now, there has been talk in physics dealing with singularities about, well, you can't ever have a naked singularity. Here, you can't ever have a naked future. Essentially, you can't see the future in this regard, and you can't see past because in our perspective, it hasn't happened yet.
Yes.
that whole new universe hasn't happened yet. It's ambiguous. But again, Hawking described black holes as ambiguous, and they really are. And it's interesting. Now, our universe being a product of another universe, are we still connected to that in some way, or has it been severed, or do we have a connection? And that universe with presumably the same physical properties as our universe, that almost guarantees. I mean, it goes to infinity, right? There would be infinite numbers of universes in that model if it really is turtles all the way down, as they used to say.
Yes. Yeah. It is like so. When Einstein created the general relativity, he believed that universe is static, which means it existed forever and it will exist forever. And then his own equations showed that universe is expanding, and Einstein didn't like it, so he created cosmological constant. He corrected his equations to try to stop the universe from expansion. Then Hubble discovered that universe is indeed expanding according to Einstein and Lemaitre, who was actually the first person who solved the Lemaitre and Friedman. They solved the equations. They said universe is expanding. Now we know that the cosmological constant, which Einstein created, might be still existing, but with the opposite sign, which means it does not stop the universe from expansion. It actually may speed up the expansion. So the universe is accelerating, and this is what we, I think, observe as mysterious dark energy. So now in my theory, I would say that yes, we have like multiverse, we have like universes creating new universes through black holes, but overall the whole picture is of course it's not static, because all those universes are expanding. And now this depends, because dark energy is still a mystery. Like recently, some observations indicate that the cosmological constant may not be the explanation of dark energy, because dark energy might be decreasing in time. So this is quite interesting. So I have to think about it more. But basically, so our universe is the only universe we have right now, because we cannot see the other universes in black holes because they are not born yet. And we cannot go back to our parent, because first we would have to find this one and only one white hole, and then we could still not go back. We might see maybe things coming out to our universe, but we cannot go back. So our universe is the only universe we have at our disposal. However, in this global picture, if we consider all these timelines, like if we analytically continue our time to those timelines in those new child universes, then the whole picture is basically a multiverse, but we can be only in one universe at a time. If we want to go to another universe, we can go to a black hole, find ourselves in a new universe, but then we would have to forget about our original universe because it would be gone for us. Then that new universe would be our one and only one universe. But in the global picture, we have like basically universes creating new universes. So it's not static, but in the global picture, it looks like a constant procedure. So this process is happening forever. I believe so, because maybe it's not true. We would never know, because maybe those universes were being created by parent universes forever. Maybe there is no beginning and no end of this process. We are just in one of those cycles, but we don't know. I believe that this happened forever and will be happening forever. So this global multiverse is basically like a constant in the stationary sense, that this process is happening forever. So this kind of generalizes Einstein static universe into this like a static mechanism, which is basically always there, and those universes being created.
Now, there is also the question of determinism or non-determinism. In other words, when a new universe is born through a black hole, is there room in the framework here for it to be identical to the universe that spawned it, meaning that the same thing happens and that there are infinite universes or billions of universes branching off from our black holes, and if you go through one, you find exactly the same thing, the same timeline playing out in every universe? Or would it be non-deterministic and it would just be something different everywhere you went?
I think that there is almost zero probability that in a new universe we would exist like in another copy or like another formation. I think that a universe has so many degrees of freedom, so many possibilities, that I don't think it's a very small chance that we could find another Earth like in the child universe. So there's too many possibilities, so the probability is almost zero. So now, of course, there are some interpretations of quantum mechanics. So it is still, quantum mechanics is very beautiful theory, but still there are various interpretations of quantum mechanics. So there is a standard interpretation that everything on atomic scale is probabilistic, and we even cannot define the position or momentum of an electron before we can detect. And once we detect it, then somehow electron was collapsing, the wave function of the electron collapsed from being everywhere to being exactly at the location we detected. And this is like a most believed interpretation, the so-called Copenhagen interpretation formulated by Bohr. But there are other interpretations which sound like maybe more logical for us, like, for example, a pilot wave interpretation that particles don't exist at different locations at the same time. They only exist at one location, but they move on complex waves given by Dirac or Schrödinger equation, and they behave like waves, not because they are waves, but because they are guided by waves, just like surfers are guided by ocean waves. So this kind of interpretation. And there was another interpretation called many universes interpretation, that we exist in infinite number of copies, and there's like a lot of copies of our universe, and this probabilistic interpretation is explained basically that when the experiment is created or done to measure where the electron is basically infinite number of copies in different universes, but somehow when we measure it, all these copies disappear except the one which we measure. Or maybe those other copies are still there, but someone else will detect that electron in a different position in another universe. So there is this interpretation of quantum mechanics, but I don't think it is, I think, a good interpretation, because it requires belief that we exist infinite number of copies. And this is kind of a little, for me, unrealistic. I believe that we exist only in one copy in our universe, and there is no other copies of us, identical copies in other universes. Those other universes will have something different, and maybe if we go there, we will find something similar to Earth, but we will not find identical copy of another Earth or another us.
Now, hypothetically speaking, say the one white hole, the singular white hole, exists somewhere in this universe. Could an alien civilization from the previous universe, the parent universe to this one, travel through that and come and be present in this universe?
Theoretically, yes. Theoretically, yes. Now, of course, when this white hole is probably far, far away from us, so if we observe, let's say, if we discover that white hole and we observe it and we see something coming out, then we have to be aware that that motion happened long time ago, because we see this image of this process from the very, very past. So maybe those aliens could be even closer to us. So we observe them, and then suddenly they are on Earth. So it is possible.
Now, of course, we have a pressing problem. There are the universe, the lifetime of the universe is finite, and it only has many trillions of years left before the stars start burning out and the black holes begin to evaporate. Well, can we simply escape this universe when we want to by going through the black hole? And if we did go through the black hole, would we appear at the beginning of that universe or at some arbitrary point in time in the life of that universe? In other words, is this an escape route for us when the stars start burning themselves out?
This is an excellent question. Actually, I have to admit I'm still in the process of calculating. I don't know the answer yet to the question whether when we go to the black hole, will we be participating in the creation of the new universe, or will we see a new universe already there? It could be cold and nice, so like we could live there, or maybe it could be still hot and like young, and it would be impossible to live there. So I don't know the answer to that yet. I'm working actually on that question. But if the calculations show that if we go to the new universe, we may see already a universe being formed. And now I don't know even how old that universe could be, but if a new universe on the other side of the event horizon of a black hole is good and already big and dark and has some stars there, then we could go there and live there. So this potentially could be an escape from our universe, because yes, our universe at some point will be darker, colder, all the stars will burn. There will be no more new stars being formed because the density of matter will be too small. So there will be less hydrogen. It will be more, the density will be much smaller. So the new stars will not be forming, and it's like the universe will come to death. Like it will be infinitely cold. I mean, not infinitely. It will be hugely cold and dark, and nothing will be happening there. Now, but this is only a scenario if we have dark energy, because if our universe was formed by a black hole, then it is a closed universe. A closed universe is like a universe, like on Earth, when we travel to the east, we can go around the world and come back to the same point from the west. If you go north, you can come back to the same point from the south. And this only works in two dimensions, like in two perpendicular independent directions. If we go up, if we go away from the Earth, like we would not think that we could go back to the Earth from the other side. But if our universe is closed, this coming back works in three directions, which means XYZ. So if we keep going in one direction, then eventually we theoretically could come back from the opposite direction. This is the closed universe. Now we will never be able to actually do it because universe is expanding. So we will be too slow to do it. So, but if universe stopped expansion, theoretically we could go around the universe and come back to the same point. We could leave the Earth and come back to Earth from the opposite direction. But so our universe is closed. But the problem is that if dark energy is constant, then, and if it's big enough, then if cosmological constant is big enough, then a closed universe will be expanding forever. However, if cosmological constant is not big enough, or if it's decreasing, and this is what recent observations show, that maybe dark energy is decreasing. If dark energy is decreasing, then if our universe was born in a black hole, it is closed universe. And if dark energy is decreasing, then there is the possibility that our universe may stop the expansion because Friedman equations of cosmology, if there is closed universe without cosmological constant, would have to start contracting, would reach some maximum size and start contracting to another big bounce. So if dark energy is decreasing, then actually our universe may start at some point contracting again and would become hot and dense. Now, of course, in this case, the escape would be still advised because once we go to a black hole, then you are already in the new universe. So what happened to our universe would be irrelevant because we would be already in our new universe and we could survive, we could escape in any scenario, either if universe becomes too cold or if it starts collapsing again and becomes too hot. We would have to go to a black hole and escape, but I need to calculate whether we would be seeing a new universe already there waiting for us, or whether we would be participating in the creation of new universe, which would be a disaster because that participation starts from the very, very hot initial condition.
I do not envy a civilization that has to look forward to a big crunch. When the universe begins to compact down and collapse in on itself and get hotter and hotter and hotter, it is a universal extinction event. Any life anywhere in the universe during such an event goes extinct.
Yes,
actually, quite a ways before. Once it just gets too hot, and then eventually stars and all that start getting really close to each other. High radiation. I mean, it's just insane to think about it.
Yes.
But the sad thing is that if you try to escape it and you go through the black hole, it would be a real shame if you were stuck in a big bang because it's just as bad.
This is bad. So when, like 20 years ago, when observations seemed to indicate that we are in a universe which probably will be expanding forever because dark energy is cosmological constant, and it's already, the universe is big enough that dark energy is now dominant force, so it will oppose this attempt to recollapse because closed universe wants to recollapse, but dark energy oppose that. And if dark energy is big enough, then it wins, and universe will be accelerating expansion forever. But now the DESI observations seem to indicate, it's not yet like confirmed, but it is like they favor the hypothesis that the dark energy is decreasing. But we haven't observed this decrease for enough time to specify how it's decaying and why it is decaying. But it may be that maybe this dark energy is decreasing a little, and maybe it will stop decreasing at some point, and maybe in 10 billion years somehow this dark energy will be asymptotically tending, it will become more of a constant, and maybe after all our universe will never recollapse. So we don't have enough information yet to see what will be the fate of our universe. Will it recollapse or will it expand forever? We don't know it yet.
Is there a way for other universes, and say we're not the only one that's in existence right now, and there are other bubbles out there that were created by the previous universe's black holes, can the two universes interact with each other? And I say that specifically because some people have theorized cold spots in the cosmic microwave background radiation might represent collisions between universes. Might that be evidence of this model, that the multiverses we know at our iteration of it might interact with other like universes that also descend from the same parent universe?
It could. In fact, actually, I remember that I was in some elementary school in Poland, and one kid asked me that question, "Professor, what happens if you have two black holes which are merging? What happens to the universes inside them?" And I said, that's a wonderful question, because now now it will help me to answer your question, because when two black holes are merging, because we have mergers, in fact, most stars are like double systems. So a lot of black holes have like some companions. And we may have two black holes like orbiting each other, and this is how we can actually produce very strong gravitational wave signals, and that's how we can detect those mergers. So when two black holes are merging, then they will not be spherically symmetric. Well, even as a black hole which is rotating, all stars, all galaxies rotate. Like the creation of angular momentum is like very natural. You can make rotations like very easily by colliding two objects, not at head-on collision, but a little off. So after the collision, they will start spinning. So angular momentum is created in the universe naturally. So everything is rotating, which means black holes are not exactly spherically symmetric. And actually, they rotate quite quickly. Most black holes whose rotation was measured, they seem to rotate almost at the maximum speed they are allowed to rotate. So those black holes are already deformed from spherical symmetry, which means the universe on the other side of the event horizon of a rotating black hole will not be spherically symmetric. So there'll be some kind of preferred axis in the universe, which is inherited from the axis of rotation of the black hole, which created that universe. But if you have two black holes merging, then the same thing will happen. Those both black holes will be deformed because they'll be attracting each other. So those event horizons won't be spheres anymore. They'll be like, it looks like maybe two droplets of water wanting to become one droplet of water. So those black holes will be deformed, which means universes in those merging black holes will be also deformed, and maybe the cold spot in the universe, or maybe those are the regions which indicate some anomalies in the cosmic microwave background radiation. There may be some indications that our universe is interacting with another universe, and this interaction basically reveals itself as the deviation from the spherical symmetry of our universe. And eventually our universe would merge with the other universe, because those two black holes would be merging, and suddenly we would see that our universe is now much bigger, because we would get an access to another universe. So basically our universe would merge with a sibling. So we can never see how our parent universe looks like, because we would have to go find the white hole and go back, and we cannot do it because the motion is only one direction. So only parent can send signals to the child, not backwards. But the parent could have created another universe, which would be our sibling, and we could merge with the sibling. And even if we don't merge with the sibling universe, we could still interact with this, and this would be seen as those anomalies in cosmic microwave background radiation.
And all the people if there are anyone there in the previous universe that spawned the binary universes, all they see is a binary black hole system.
Yes, yes.
And that's it.
Yes.
And that's us. It's fascinating. And I wonder, though, to go back a little bit, you were talking about how this is an infinite process, meaning this has always occurred. We're just an iteration of something that has gone for the whole time. But I would wonder, what set those values, though, originally? What set the so-called fine-tuning if there wasn't an originating event that sparked off the creation of these universes? Any ideas on that?
So this is, fine-tuning is very interesting problem, because there are three fundamental constants of nature: speed of light, gravitational constant, and the Planck constant of quantum mechanics. Now, those three constants by themselves, there's nothing special between them, because those constants can be used to define the units we measure the universe, which means meters, kilograms, and seconds. So we can always change the units of the mass, length, and time, and all these three fundamental constants will be all equal to 1. And those units are called Planck units. However, we have, for example, elementary charge of the electron. And this is fascinating, because when we take the square of elementary charge of the electron and we divide it by Planck constant and speed of light, then we will get something which has no units will get a number, which is called fine structure constant, which is like approximately 1 divided by 137, which means that constant is actually quite interesting, because if that constant was, let's say, twice bigger or twice smaller, and that's a number. Number means that you cannot change it by using different units like meters, or go from meters to feet, for example, or inches. That number will stay the same no matter what units you are using. And that number, if this number was twice bigger or twice smaller, then we might see things like maybe hydrogen could be unstable, or maybe more helium, or something. The chemistry might be different. So it looks like that there may be some kind of fine-tuning in this creation of this number 1 of 137, which comes because we have this fourth constant. We have the electric charge of the electron, which is the elementary charge. So the existence of that, and also there are some other constants, like, for example, the ratio of mass of proton and electron. This comes from some combination of electromagnetic weak and strong interactions, but no one knows, because there's no derivation of masses of elementary particles. We don't know where they come from. So there may be some fine-tuning. However, when I hear some arguments about fine-tuning, they say, oh, if gravitational constant was twice bigger, then stars would have formed much faster, and maybe there'll be not enough time to do something, so there may be some instability. So like, there may be some different arguments that our universe might have looked differently. But those arguments only say, if we change gravitational constant by a factor of 2 and we leave all other constants the same. But maybe there is some fundamental theory of gravity and quantum, and maybe some fundamental physics which somehow connects all these constants. Maybe elementary charge of the electron, maybe this 100 over 137, this fine structure constant, is a solution of some numerical equation which combines a lot of constants together. In this case, if those constants are somewhat related to each other through some equation we don't know yet, then if we change a value of one constant, we might also change values of other constants according to that equation we don't know. And since we don't know the equation, I don't think we should speculate what would happen if we change gravitational constant by a factor of 2, because maybe other constants, maybe Planck constant at the same time would have to be changed by a factor of, let's say, 4. I don't know. So we don't know the equation, we don't know the fundamental physics combining those equations. So all these fine-tuning arguments are not complete. We don't know, and we don't know everything about those constants. So we cannot really determine how those changes, what would happen with those changes, because other changes might be happening at the same time, and we don't know yet which ones.
In other words, it may simply be, with all the constants piling up, the answer may simply be, it's the only way it can be. This is the only way that a universe can end up, in short.
It may be. In fact, actually, this is how I liked Smolin's hypothesis, because his hypothesis was saying that because of singularities, the constants can be changing during the transition from the final singularity in the black hole to the initial singularity in the new universe. The constants could be changing, which means universes, our universe will produce billions of babies, because we have billions of galaxies, and each of them has a black hole at the center. So technically, all black holes will create new universes. So our universe creates billions child universes. But if singularity was okay, then those universes would have different constants. And the universes which made good constants, similar to our constants, they would themselves create new black holes, which could be creating new universes, and the process would keep going on. And the universes which would choose randomly during this transition at the singularity, if they changed those values of constants to some different values which would not be the best ones, maybe those universes would end up being not very good universes for the creation of black holes, stars, and then black holes. And maybe those universes would have no children. So basically the process would not continue, which means the process. So in Smolin's hypothesis, universes which continue the process of creation of new universes would be the ones which would be creating universes with good constants. And maybe they don't have to be the same constants as our universe, because maybe different constants would create a universe which would be different from us. Maybe there will be something which we even cannot imagine, maybe some new life. Maybe there will be like 500 chemical elements instead of like 100 we have right now. Maybe there will be the ratio of proton to electron will be different, but it would allow some other composite particles to be formed. Because right now from quarks, we can have only mesons and like baryons, like two quarks, a quark and anti-quark, or three quarks or three anti-quarks. But maybe with different constants, we might have systems which have like maybe, I don't know, 7 quarks or something. I don't know. So this may be different universe. However, this is just with the singularity. I believe that the singularities are unphysical because nothing can be infinite, because physics only can measure finite quantities. So if we talk about infinities, then it becomes not physics, it becomes like mathematics. So I want to stay in the domain of physics. So I want to make I believe that all physics is finite, everything is finite. So singularities don't exist. Infinities in quantum field theory don't exist. So this renormalization must be corrected. And I believe I even wrote 2 papers, 2 articles showing how torsion can also eliminate infinities from quantum field theory. So the ultraviolet divergence is also gone. So I believe torsion can remove infinities not only in general relativity by avoiding singularities, but also can fix quantum field theory. But basically, I believe that constants of nature are the same in all universes, because all the bounces were continuous processes. So maybe just from the very, like forever, maybe we are living in universes with those constants, which basically are good enough that they produce new universes. And why? I don't know. I don't know, because if this process was happening forever, then I don't know. Also, we could ask the question, what maybe if there was the very first universe who was starting creating those black holes and then Chilean universes and then more. But then if we assume that, then the question would be, what was before? So this hypothesis, this scenario would create more questions. So for me, the simplest hypothesis is that this process has been happening forever and will be happening also forever. So there is no question what was before and what will be after.
Now, would you characterize, this is starting to remind me of something, and namely neutron degeneracy pressure in a neutron star and degeneracy pressures. Could you say this new torsion is a new degeneracy pressure? Could you characterize it that way, or would you term it differently?
This is very interesting analogy, because yes, the pressure in degenerate neutrons allows neutron stars to exist. So otherwise they would have to collapse further and they would inevitably become black holes. But in fact, neutron stars cannot be too massive or too big, because if they are big enough, if they have enough mass, then the gravity wins and they will become black holes. But degenerate pressure in neutrons and also degenerate pressure in electrons, which is a little smaller. So it creates white dwarfs. So electrons can be degenerate and we have white dwarfs. And for least massive stars, that's how they end up. And more massive stars end up as neutron stars when neutrons are degenerate. And the most massive stars, they have no choice, they have to become black holes. But torsion could be considered as some kind of analog of degenerate pressure, because it prevents gravitational collapse to reach a singularity. Except that this pressure would always win, because what happens is that this analog of degenerate pressure coming from torsion, it is proportional to the square of spin density. It's an average spin square density. So what happens is that when the matter collapses into the black hole, so the density of matter will be growing more slowly than that analog of degenerate pressure coming from torsion, because that pressure is now proportional to the square of the matter density. So curvature will be growing linearly with the density of matter, but torsion, which opposes curvature, which gives a gravitational attraction, will be growing with the square of the density of collapsing matter. So torsion will be growing faster than curvature. Of course, initially torsion is very, very weak. So even on Earth, or even in neutron stars, we don't have to worry about torsion. Torsion is only significant at densities approximately 10 to the power of like 45 kilograms per meter cube, which is much higher than neutron stars. So on Earth, in solar system, in galaxies, in neutron stars, we can ignore torsion. But in black holes, when the densities of collapsing matter can become much bigger than nuclear densities or neutron star densities, and they will reach this 10 to the 45 kilogram per meter cube, then torsion starts becoming strong, and it acts like this kind of degenerate pressure, and it will always win. So the singularity will never be formed.
There's an elegance to it, though, because gravity is like that. So gravity in quantum mechanics, gravity is barely there. It's not really even a concern because it's so incredibly weak. But you get enough mass together and gravity eventually becomes a black hole.
Yeah.
So it sort of mirrors it in a way, right?
Yes. Here, actually, thanks to torsion, which is produced by intrinsic quantum spin of particles. So actually, here the quantum mechanics, which makes spin, and spin through Einstein-Cartan equations makes torsion. So it is basically quantum mechanics and gravity together, but it's not quantum gravity, because I believe that space-time is classical, like at the fundamental level, but spin is quantum a quantity living in classical space-time, and spin can create classical torsion, and the torsion basically is a gravitational repulsion. So it is quantum mechanical quantity which can beat gravity, well, one part of the gravity, because normally gravity is viewed as curvature of space and time, and it's always attractive. But in this modification, space-time has also torsion, and torsion actually is another part of space-time which is there. It was assumed to be zero for simplicity, but torsion and curvature are two quantities which describe space-time. So if we don't ignore torsion, if we allow it to exist, then this torsion is normally very weak anyway. So we don't need that to change physics on Earth. But at high densities, torsion becomes big enough, and it acts like anti-gravity. So curvature is gravitational attraction, and torsion is this another gravity, which is gravitational repulsion. And at extremely high densities, thanks to quantum mechanics, torsion beats curvature and prevents singularities.
So in the model of singularities, a black hole is a singularity, there's the idea of a Kerr ring, where the rotating black hole can actually form a ring of sorts in the black hole. In this torsion model, would that also happen? And would you have a sort of situation of a donut inside the event horizon?
Oh yeah, this is an interesting question. I have not yet considered what happens to the collapse of matter inside a rotating black hole, because mathematics would be too complicated. But this is what I want to do, because we know the Roy Kerr solution of a rotating black hole, which generalizes Schwarzschild solution of a static black hole. So Kerr black hole has two parameters. There is the mass, just like in Schwarzschild metric, and we also have the angular momentum of the black hole, which can be divided by mass of the black hole and speed of light, and it becomes something called Kerr radius. So rotating black holes are described by two parameters, the angular momentum and the mass. Technically, we could have the third parameter, total electric charge, but it's almost zero, I think. But technically, we could have charged black holes, Reissner-Nordström or Kerr-Newman metric, and so we have three parameters now, which is the same number as elementary particles. Elementary particles also have spin, which is angular momentum, mass, and electric charge. So black holes and elementary particles are two kinds of the simplest objects in the universe, because they are described only by three numbers. And everything between is more complicated because you have more numbers to describe. But what would happen, so I have not done any calculations, they are too complicated, but I think at some point I will start to think about something. But conceptually, like qualitatively, I would think that, so a singularity in a rotating black hole, according to standard general relativity, is a ring. Now, and this ring is the set of singular points. So there is those points on the ring, which is infinitely thin, they would have infinite curvature and infinite density. And even some physicists were thinking, oh, even if the singularity, a ring singularity forms, maybe some particles could go through this ring, don't touch the ring, and go somehow through and maybe be on the other side. So even this idea of new child universe could be there, except that some particles would hit the singularity, so they would not end up in the new universe. Now, if the torsion modification is correct, then that ring, that singular ring, would be replaced by the donut. It would be a donut which would be thin, but not infinitely thin. It would be a non-singular torus, like a donut, which so the matter would become a donut eventually, and then it would have to expand back. So this donut would be expanding, and now I don't know how it would end up with. Some people believe that our universe is a giant donut, that you can go around the universe, and so it is possibility. But I think that if that donut would be expanding, then probably the inner radius of the donut would probably, the donut might have end up as a sphere eventually. So, but I don't know. It is an interesting analysis. I haven't done that yet. But maybe this donut would become a huge donut, or maybe the donut would end up as a spherically symmetric or almost spherically symmetric universe, because it would have to inherit the axis of rotation. So there will be some asymmetry in our universe. So I don't know. It is an interesting idea.
Now, going to no-go universes. So as we were talking earlier in the conversation, going into a supermassive black hole, you wouldn't even notice that you passed the event horizon. You'd only notice if you tried to get out. But the sticking point here are the really nasty stellar mass black holes, where you get spaghettified and destroyed as you near the event horizon. Are those universes forever inaccessible because you just get destroyed before you get near a black hole of that mass?
They would not be accessible without destruction, because like a black hole which has mass on the order of magnitude of mass of the sun, or 10 times more massive, then the calculations show that those tidal forces, when we, let's say, put a human with a person with the height 2 meters, and we calculate the difference between gravitational force of attraction acting on feet and acting on the head, then the difference is can be like million newtons or billion newtons. So it is a very big one. So the person will be stretched, and yes, spaghettification. So so technically spaceships and with people cannot go through such black holes. So they won't be accessible for us. They might be accessible for some devices which are resistant to millions of newtons. They could go there, but if they go there, they will not have people there, obviously. So computers maybe could go there, but they cannot send any signals back to us, so it will be probably useless. So we will never know what those computers who managed to survive spaghettification would see on the other side. But the hope is that maybe those little black holes, they could eventually become big enough. When they eat enough matter from outside, they can become big enough, and the mass will be growing. So they might be bigger black holes. But this is probably not very realistic, because usually those black holes made by stars are like lonely. So they cannot maybe eat too much. They would have to become supermassive black holes to be accessible for humans. And supermassive black holes, they only can form at the centers of galaxies, where you don't have to squeeze the matter to make a black hole, because the Schwarzschild radiation for a black hole tells us that mass and radius are proportional to each other. If we also try to calculate the density of a black hole, then like an average density, if you take the mass of the black hole and divide by radius, we know that the mass is not everywhere, but if you kind of want to find the mean density of a black hole, then you would take the mass and divide by cube of its radius. So when we do it, we discover then the bigger black hole, the smaller density. So for example, in order to make a black hole from Earth, we would have to squeeze it to like a size of like maybe 1 centimeter. So the density, so if you divide mass of Earth by volume of a sphere, which is like 1 centimeter diameter, then this density will be like enormous, like 10 to the power 30 something kilograms per meter cube. still smaller than torsion. Even if Earth becomes black hole, at the formation of the event horizon, torsion would not be strong yet, because it will be strong later when the matter tries to reach the singularity. Then torsion will say stop. However, if we take the black hole at the center of a Milky Way, then we find that the density of the mean density of that black hole could be like equal to the density of water or air. So we don't have to squeeze matter very much. What we need is basically a huge amount of that matter. So, for example, if we fill if you have a sphere which is as big as orbit of Jupiter around Sun, and we fill that sphere with water, it will be a black hole already, because it will have enough mass within the radius. If we take even bigger sphere and fill it with air, it will be a black hole already. So basically interstellar intergalactic dust can make a black hole if you have this dust like in a big volume. So it will be a black hole already. So big black holes can be easily created naturally, and every galaxy has one.
Which brings us to my next question is, if we created an artificial black hole, we got a bunch of matter together and created one, and would we have any possibility of controlling the parameters of it? Say we wanted the 500 elements instead of the 100 or so that we have now. If we wanted that, could we tweak a universe upon creation of a black hole to be better than this universe, better suited? And could that solve the Fermi paradox, and that when civilizations figure out black holes, they go inside of them and leave this universe entirely?
So, well, if singularities really exist, which I don't believe, but if they exist, then it's possible to change laws of physics or values of physical constants. So technically, if we ever created an artificial black hole, we technically could create a new universe on the other side of the event horizon of that black hole, which has 500 chemical elements, for example, thanks to different values of constants of physics. But if torsion exists and avoids singularities, and this transition happens smoothly, continuously, if the big bounce is regular and continuous, then we would not have new values of physical constants. So the new universe on the other side of the event horizon of an artificially created black hole would also have 120 chemical elements like our universe.
And possibly an island of stability, but that is a completely different subject.
Yes, of course.
Now, in regards to the information paradox with black holes, it seems to me, and correct me if I'm wrong, that evaporates in this model. In other words, there is no, the information is conserved by being in another universe.
Yes.
So you can't access it from here, but it just moves on through. Therefore, there is no information paradox with a black hole, right?
Yes, that is correct. So the black hole information paradox for me is superficial. I mean, if there is a singularity, then of course there is a huge paradox, because what happens, because everything in the everything according to general relativity with a singular black hole, evaporation basically would bring back to our universe everything which was on the other side, because if event horizon evaporates and there is no new universe, then everything inside the black hole will be accessible to us again, and all the radiation radiated to us in this process of evaporation will have, it looks like it has like smaller entropy, like smaller information. So information got lost, and this violates quantum mechanics. However, if every black hole creates a new universe, then all the information goes there. Now, from our perspective, it will go there after infinite time, because because all black holes are almost there, so they are not yet formed. But still, information is going there, and entropy is growing asymptotically. It will become maximum after infinite time, because after infinite time, when the event horizon forms. So from our perspective, everything is great. But then what happens is that the real matter goes through in the proper time. In their own time, they will not see any strange thing. They will cross the event horizon, and all the information which went to a black hole will appear on the other side in the new universe, And the entropy can grow further in this new universe. Information can also increase because I think they're proportional. Well, not proportional, but through some logarithmic, or maybe they're proportional. There are some theories of information and entropy. I think they are both like equal to natural logarithms of some number of possibilities. So information is preserved. It can go through. Entropy can grow further. So there is no paradox. There's no paradox.
Now, my last question for you, Doctor, is admittedly very speculative, but I have to do it. I have to ask it. What if there's a symmetry here between this universe and its black hole universes, its child universes, that flips the arrow of time, meaning that you go through the black hole and time is moving backwards in the new universe? Is that possible in this model? Because we don't really know why the arrow of time is what it is. We just know that it goes, we know entropy. So could it be reversed by going through a black hole and you find yourself at the end of a universe moving towards its Big Bang?
Now, this is an interesting question. So the arrow of time has like several kinds, because we have cosmological arrow of time, which is related to the expansion of the universe. Universe is expanding from the past into the future. We have also a thermodynamical arrow of time, that entropy is increasing. We have quantum mechanical arrow of time, then collapse of the wave function doesn't go backwards. Usually the collapse of the wave function indicates the past and the future. It collapses from the past to the future. And all these arrows of time coincide. So it is one arrow of time, but all of them are basically maybe contribute to this one arrow of time. Now, if we have a new growing universe on the other side of the event horizon, then that universe is growing. So already we have the cosmological arrow of time defined, and this arrow of time will be the same as arrow of time of the parent universe, because the matter is going, in our universe, the matter is going from the past to the future, defined at the event horizon. Then on the other side, this matter is participating in, this matter is basically in this new growing universe. And if this matter is participating in the creating of the new universe, then this timeline is basically continuing. So universe is expanding. So it will be the same cosmological. So cosmological arrow of time would be preserved. Same thing with second law of thermodynamics, because the entropy of the black hole, the entropy of the matter forming a black hole is increasing. From perspective on Earth, this entropy reaches the maximum entropy of a black hole given by Bekenstein-Hawking formula, and this entropy is reached after infinite time from our perspective. But on the other side, this entropy is growing further because there's a new matter production, so the production of matter increases entropy beyond that formula for entropy of the black hole. So entropy will be growing continuously, and since growth of entropy defines the thermodynamic arrow of time, that means that thermodynamic arrow of time will continue in the same direction. So basically, so in my opinion, cosmological and thermodynamic arrow of time will continue. They'll continue the same direction. Now, for quantum mechanical arrow of time with the collapse of the wave function, I don't know, because collapse of the wave function happens only in Copenhagen interpretation of quantum mechanics, but we don't know yet which one is correct. We may have pilot wave, the Broglie bomb interpretation. This may be realistic. So we don't know. So I don't know about quantum mechanical arrow of time. So I don't know how to answer. But I would say that probably the arrow of time would continue in the same direction in the child universe as it was in the parent universe, at least for thermodynamic and cosmological, but those are probably the most important ones. There's also a psychological arrow of time, that we don't remember the future, but we remember the past. But this is, I think, related to entropy somehow. So I think it is just, and also it requires humans. Without humans, there is no remembering, I think. So I think the psychological is related to the thermodynamic one. So I would say that, in my opinion, arrow of time would preserve its direction.
All right, Doctor, we are out of time. And I have to say, this is elegant, because singularities create so many problems in physics that have created so many arguments over the years. And if you just eliminate, and you're able to eliminate singularities and infinities from physics, it starts getting elegant looking, and it starts making to me, more sense. And this black hole theory is probably the best one I've ever heard, to be honest with you. It's fantastic because it eliminates the singularity and all of the problems inherent with black holes go away. But then you end up with a wormhole, an Einstein-Rosen bridge to another universe.
Which are as mathematical good solutions as black holes.
Yeah.
If I could say one thing,
Sure.
there is one additional thing which this theory solves, because what happens is that initially after the big bounce, and actually there may be several bounces because the new universe in a black hole initially may recollapse and then reach another bounce and then create more matter and then expand, and then it may have to recollapse again. So we may have like some number of bounces, but in each bounce there is new matter being produced. So eventually there will be in a series of bounces there will be such bounce after which universe will expand to big enough size, because the more matter we have, the more size the universe can reach. And that universe will be big enough that dark energy will take over, because dark energy is proportional to volume of the universe, and the universe will escape this series of finite number of bounces, and the last bounce will be the Big Bang of the universe, which will be expanding forever. And what is the beautiful thing about it is that the dynamics of the universe immediately after a bounce, where we have torsion and particle production, the particle production creates new particles, and those particles are repelling each other initially. So this repulsion is getting magnified by so that the repulsion produced by torsion is getting magnified by the particle production who are repelling each other. So the initial expansion of the universe, actually the equations predict it is exponential, which means it looks like inflation. So the torsion and particle production together, they can mathematically explain where the inflation comes from. And this inflation doesn't last forever, which is the biggest problem of the standard inflation theory, because theorists say that once you start inflation, it will be eternal, it will go forever, and that's not what we observe. Torsion eventually becomes weak. So the inflation will stop. This exponential expansion, this creation of new particles will stop, and inflation will end, and the exponential expansion of the universe will change into the standard expansion of the universe with normal matter. So I want to say torsion and particle production together can also explain inflation. So this is another, in addition to avoiding singularities, there is another advantage of this theory, that we can also explain where the inflation comes from, and inflation solved so many problems. So I believe it is a good theory, but now torsion gives the origin of the inflation.
So it explains the inflationary period of the universe, but would there be any evidence of this? In other words, could we look at the CMB and see maybe any evidence that might support that?
Yes. So currently inflation theories are being tested by cosmic microwave background radiation, but they are being tested by the standard model of inflation, which assumes existence of some hypothetical scalar field, and this has two free parameters, and basically cosmic microwave background radiation can test those theories. However, I wrote an article in 2016 showing that cosmic microwave background radiation can also test inflation produced by torsion and particle production. And I found that, and this has only one free parameter. So the theory which produces inflation from torsion and particle production has only one unknown parameter, which is basically the rate of production, which we don't know because we don't know completely how to combine quantum field theory and general relativity together. So we have some guesses, but I found that for a wide range of this particle production rate, the data agrees. So basically cosmic microwave background does not prove or disprove torsion and particle production explanation of inflation. So right now there is some kind of range of parameters that they are all consistent. So right now it's inconclusive. However, there are two possibilities. We may have some new, more exact data in the future. We might put some more constraints, or maybe we have to go, because cosmic microwave background cannot probe our early universe early enough, because cosmic microwave background is the oldest light in the universe, which escaped the matter when universe was cold enough, which happened like 330,000 years after the last bounce, the big bounce, which is the big bang of our universe. But maybe to test whether torsion exists and inflation was produced by torsion, we may have to, instead of using photons, we may have to use neutrino cosmic microwave background, because neutrinos can interact at hotter temperatures and can go through. So maybe if we find out the way how to use neutrinos or gravitational waves to test the earliest moments of the universe, maybe we can go more backwards in time, and maybe we can prove or disprove that torsion really exists.
And that's breaking the 300 million year brick wall that the CMB imposes on us, with the gravitational waves and the neutrinos.
Yes.
One question. In the case of this universe, there's always the open question of the matter-antimatter asymmetry. Why there was slightly more regular matter than antimatter when both should have been created in equal amounts and everything annihilated. Inside the black hole, is it possible that can flip and you can have the asymmetry the other way? And if you go through the black hole, you end up annihilating as you go into an antimatter universe.
And this is, in my opinion, the biggest mystery. This is my most fundamental question I want to answer right now. What is the origin of matter-antimatter asymmetry? Because quantum field theory shows that anti-electron, the positron, is basically mirror image of electron. They have identical mass, identical spin. The only difference is electric charge, which is opposite. And antiproton, but antiprotons are also opposite. They have opposite charge than protons, which means this mirror antimatter universe, if this was the possibility in the black hole, in the new universe formed by the black hole, then if there was more antimatter than matter, then technically it would be the same universe as ours, because we are made of matter, but we are surrounded by protons and electrons. So if the mirror universe produced more antiprotons and anti-electrons, the relative relation between them would be the same as the relation between protons and electrons in our universe. So this antimatter universe would behave probably the same way as our universe. So basically, for them, matter would be extinct. For them, matter would be a very small percent, and antimatter would be dominant. And if the symmetry is exact, if all the laws of physics do the same thing for matter and antimatter, then this anti-universe, we can call this anti-universe, I mean, it would look the same as our universe. Now, antimatter can also interact with matter, but well, if this new anti-universe is like disconnected, I mean, there is this white hole connecting them, and that's it, then the antimatter in that universe would not interact with matter in our universe, so there'll be no danger or anything. So it's possible that this new universe could be mainly composed of antimatter. But I want to, before like even investigating this, I'm investigating actually whether torsion could be responsible for generating matter and antimatter asymmetry. And I even wrote an article like in 2000, I think, 11, actually making some preliminary calculations, and I suggested that torsion might be responsible for matter-antimatter asymmetry in the early universe. Not anymore, because now torsion is almost zero. So on Earth, we would not see any asymmetry, like any different behaviors. But I believe that at the very early universe, when torsion was big, there was some asymmetry between matter and antimatter, and maybe somehow because of that, more matter was created than antimatter, or maybe they were created at equal amounts, but somehow more matter survived than antimatter. So, but I'm still working on this. This is, in my opinion, the biggest, this like the most like puzzling question for me, where this asymmetry came from. I believe torsion could do it, but I want to find out how it happened. So I don't know yet, but I'm working on that.
I got another one, the anisotropy of the universe. In other words, why the minute temperature differences that caused matter to clump? What caused that? Is there anything in your hypothesis that might explain that? The temperature variations of the CMB?
Yeah, temperature variations. So the standard model says that those are quantum fluctuations of matter which were amplified during inflation, and they were very tiny and they become very big. And so I would say that, well, in the presence of torsion, I mean, there are still quantum fluctuations of fields and they would be amplified by torsion. So I think that in the presence of torsion, those little tiny quantum fluctuations of matter got amplified by inflation, and they became the fluctuations of temperature in cosmic microwave background. And then they got amplified even more. And now we have voids or regions of the universe with a lot of superclusters of galaxies. But I think that in the presence of torsion, the overall picture would be the same, that quantum fluctuations got magnified. The only thing would be that torsion gives the explanation where the inflation came from and why it ended. But torsion would still predict inflation, and that inflation would still amplify those tiny quantum fluctuations into temperature fluctuations in the cosmic microwave background.
Doctor, thank you for joining us today. This was about the most fascinating conversation I've had in a very long time, and a very compelling idea that seems to solve a lot of outstanding problems.
Thank you.
In a way that's actually less surprising than those outstanding problems are. Things like, singularities are not good. And yet, they just go away here and physics just becomes very normal. Nothing abnormal, nothing infinite. And it's predictable. It's very nice.
I hope so. Thank you, John.
Thank you, Doctor. And I hope you will come back as your work develops and we'll have further conversations on this.
Thank you very much.